Greetings everybody. So today we are going to discuss about our new topic, which is effect of pressure and temperature on solubility. First, we need to understand what is the terminology solubility. We know that whenever we add a solute into a solvent, whenever we add a solid solute, let's suppose we have a crystalline solid solute and we have added that into a solvent, right? So once we have added that crystalline solid into the solvent, that crystalline solid will now, it is basically in a crystallized state. If we talk about a crystalline solid, let's suppose we are taking NaCl. NaCl is a crystalline solid, and here that crystalline solid, when dissolved in the solvent, which is water, let's suppose, will now be having um, will now, when it will be dissolved, it will tend to now dissociate. It will tend to dissociate into its ions. Such as we are taking crystalline solid, and that crystalline solid, when is dissolved, it tends to dissolve into the solvent, and as it tends to dissolve within the solvent, it is basically decrystallized from its crystallized state. Previously it was recrystallized, after which when it was dissolved it became dissociated, and thus this state was known as decrystallized state, in which it was found in the form of its components or its ions, sodium and chloride ions. This state was known as decrystallized state, and this phenomena is known as decrystallization, right? Decrystallization. Now, when decrystallization occurs, it can also be called a dissolution, as we have previously studied the enthalpy of dissolution. As in this case, the enthalpy of dissolution would be produced as well, right? So, enthalpy of dissolution, right? Okay. So here, when the crystalline solid is dissolved into the solvent, now as it is present within the solvent, it will now tend to being it's basically having in the ionic form. In ionic form, it is basically having charged species. In ionic form, it is a charged species. In ionic form, it is a charged species, which means that as a charged species, it will tend to have kinetic energy. Tend to have kinetic energy, and with regard to that kinetic energy, it will now tend to move within the solution. It will now tend to move within the solution with a uniform motion, as a result of which it will be uniformly distributed within all parts of the solution, due to which it will form a homogeneous mixture. And that homogeneous mixture is what we call as the solution itself, right? So once the solution is formed, uh, there will be a state when we'll be adding further solute, and addition of further solute will cause to increase the quantity of the ions. As a result of which, as the quantity of ions is increased, it will lead the ions to increase their collision rate, because more ions will be moving here and there within the solvent due to the high kinetic energy, due to which their collision rate will be ultimately increased. As a result of which, some of the ions would turn out from their decrystallized state or from their ionic state, due to the collision occurring between them, back into their solid state, and that solid state would be again the crystalline state, which would be sodium chloride. And now sodium chloride, which is formed after the decrystallization, is now known as the recrystallized state. First, there was a crystallized state which was decrystallized, due to which after decrystallization there was recrystallization in order to form a precipitate, which was known as the sodium chloride once again. So this process is known as recrystallization, or in other words, we also call it as the process which is known as precipitation, due to, because in this case there's formation of precipitates, right? Now there comes a state when we keep on adding the solute within the solvent, and this process ultimately causes once to increase the rate of recrystallization, and gradually, as the rate of recrystallization keeps on increasing, the decrystallization rate of decrystallization becomes equal to the rate of recrystallization, which means there will be a formation of a dynamic equilibrium. And that dynamic equilibrium which is formed between the rate of decrystallization and recrystallization will be considered as the position of the solution in which it will be having the maximum concentration of the solute in that solvent, and that's maximum concentration of solute at that solvent in which the solution is in equilibrium with its solid phase is known as the saturated solution. In which the solution is in equilibrium with its solid state is known as the saturated solution, right? And that saturated solution, right? Saturated solution. And that saturated solution now at a constant temperature, as we are having the saturated solution, we can now define solubility as the state at which a solute has maximum concentration its maximum concentration within a solution at a constant temperature, which is known as the solubility. Now the capability of a solution to form saturated solution is known as solubility of that solution. Now in that case, if we talk about saturated solution now will be basically have its characteristic which is known as solubility, such that when there is maximum concentration of solute in a particular solvent at a constant temperature, then this maximum concentration or maximum capability of that solution to produce a saturated solution is known as the solubility of that solution, or the maximum concentration of the solution to contain the maximum amount of solute within it is known as the solubility of a solution, or the capability to of the solution to stay in equilibrium with the solid phase at constant temperature is known as solubility of the solution, right? So in this way we can just clear out the definition, right? And after that, when it comes to saturated solution, we can solubility, there are several solubilities for different compounds. When it comes to sodium chloride at 0 centigrade, for sodium chloride the solubility is 37.5 gram out of 100 gram of water. While when it comes to copper sulfate has its solubility varied with temperature. Actually, solubility varies with temperature, such that if we increase the temperature, most of the time the solubility is increased. But there are some exceptional cases in which solubility also decreases with the increase in temperature. So we are going to discuss that as well, right? And after that, um, when it comes to copper sulfate at 0 centigrade, its solubility is 14.3 kilogram, 14.3 gram out of 100 gram of water, and at 100 centigrade it is 75.4 a gram out of 100 gram of water. So this is what we considered as their solubility, right? And these were some examples. Now in order to find the solubility, we can just try an experiment within the lab, such that if we take a solution, a saturated solution, right? And afterwards, when we filter that solution out, and then evaporate it on a petri dish or a china dish, then the amount of solid remnant or the solid particles which would be left out would be considered as the amount of solute which was dissolved in the solution, due to which it would be utilized in order to find the solubility of that solution, by simply writing is it as the number of grams of solute per dash grams of the solution, number of grams of solute per 100 grams of solvent, or whatever the concentration of solvent is, we can write it accordingly. So after that, when it comes to some important parameters on considering solubility is affected by temperature as well as pressure. First effect is known as temperature. Now when it comes to describing the temperature has effect such that most of the time the solubility increases with an increase in temperature. But there are certain cases in which we are having exothermic reaction. Whenever there is an exothermic reaction occurring within the salt, whenever there is an exothermic reaction occurring, then that exothermic reaction, let's suppose if we take an example of solution which is known as cerium sulfate. Cerium sulfate is a solution. Now cerium sulfate is a salt. When we dissolve cerium sulfate into solvent water, so at that moment it will tend to perform an exothermic reaction, which means its enthalpy of dissolution would be negative. As its enthalpy of dissolution would be negative, it will now tend to perform an exothermic reaction, and that exothermic reaction will now tend to release energy, heat energy from the intermolecular forces of attraction from of the solvent as well as the solute, due to which the intermolecular forces of attraction as will have the amount of heat energy decreased, will have their stability increased and reactivity decreased, due to which they will now tend to ultimately decrease the volume of the solution, as a result of decrease of volume of the solution there will be a decrease in the solubility of the solution as well, such that as there is decrease in volume of the solution, the solubility of the solution is ultimately decreased. Decrease in volume leads to decrease in solubility, because if we are decreasing the volume, ultimately the quantity of solvent is decreased, due to which the solubility is ultimately decreased. But when it comes to endothermic reaction, we will be having opposite of it. In endothermic reaction, if we talk about let's say if we talk about potassium chloride, potassium chloride is basically having its dissolution energy, enthalpy of dissolution as positive. Enthalpy of dissolution is positive. As a result, enthalpy of dissolution is positive, due to which it will cause to form a reaction. Enthalpy of dissolution, enthalpy of dissolution positive, right? So here enthalpy of dissolution is positive, which means endothermic reaction would be occurring, due to which heat energy will be gained in order to weaken the intermolecular forces of attraction, due to which when the intermolecular forces of attraction will gain the heat energy, their stability will be decreased, reactivity will be increased, due to which they will become less stable, and thus it will cause to increase their intermolecular gaps as a result of weakened intermolecular forces, due to which their volume will be increased. As volume will be increased, there will be an increase in the solubility as well. So in this case, this is how we consider it. And these were some parameters about it. Now, apart from that, if we talk about the graphical representation of the solubility can be defined in two ways: continuous solubility curve and discontinuous solubility curve. First and foremost, graphical representation of temperature's effect on solubility is known as solubility curve, and that is of two types: continuous solubility curve and discontinuous solubility curve. Continuous solubility curve is normally for crystalline solids which are without hydrated form, which means there's no hydrated form within their structure, such that if we talk about potassium chloride, there is no water molecule within it, no water molecule within potassium chromate, heptachromate. There's no structure within it as well. So these are some solubility curves. These solubility curves show a single phase, which means there's a single phase of theirs, and that single phase, they have a single phase, and that single phase shows a continuous either decrease. That single phase either shows a continuous decrease or a continuous increase in the temperature, with respect to increase or decrease in the solubility. So in this case, uh, this shows a continuous increase or decrease, such that there is no break in between the graphs, such that if we talk about discontinuous solubility curve, there's a break. As you can see, this graph is quite straight in an exponential manner either, or in a linear manner, but the graph which is discontinuous is having breaks, such that here there's a break, and from here there's a new phase starting with a new solubility. So in continuous solubility curve, we have a continuous solubility, a single solubility of a single compound, right? So if you consider potassium chloride, potassium chlorate, potassium heptachromate, as well as lead nitrate, calcium chloride, all of these are having a positive correlation with the increase in temperature. If we increase the temperature, their solubility is also increased. But if we talk about sodium chloride is having a minimal change in its solubility by increase of its temperature from 0 centigrade to 100 centigrade, which means there's a minimal change. But when it comes to sodium sulfate, it has a negative correlation, which means it performs an exothermic reaction, and thus it is having has an decrease in solubility before 40 centigrade, before 40 centigrade, decrease in solubility before 40 centigrade with an increase in temperature, And after 40 centigrade, the change in solubility remains constant, which means there's no change in solubility, right? So change in solubility remains zero, and their solubility remains constant with increase in temperature. Now these are some considerations. Apart from that, when it comes to dissolubility curve, it basically a discontinuous solubility curve. Discontinuous solubility curve basically involves the major characteristic of hydrated crystals, such that, as you can see, all of these compounds which are mentioned in the diagram are also hydrated crystals. These hydrated crystals are basically having water molecules, such that if we keep on providing them high temperature, as the temperature is increasing, let's suppose calcium chloride dot 6H2, right? So here, at first, when the temperature is increased up to 30 centigrade, there is a particular solubility curve, and after that particular solubility curve, there is the break. There is a break between the solubility curve, and that break in the solubility curve leads to formation of another curve from here, which ultimately gives a new solubility and a new phase, right? So in that case, it is basically a single solubility curve which is made up of two or more than two solubility curves within the single discontinuous solubility curve graph, right? Now, as you can see, as calcium chloride is having 6H2O, after the formation of a new phase, it loses two of its H2O. Two H2O are lost, and it forms a structure which is known as calcium chloride dot 4H2O. So these 4H2O, which are released in this case, now will have a different solubility with an increase in temperature, due to which that different solubility with an increase in temperature will lead to a new phase with new properties and new composition. After that, when it will further go upside, it will again break has a it will again have a break over it, and once the break is done, it will now tend to uh, continue its formation of solubility, and its solubility will be new. At that point, there will be a new phase arisen from this point, and will ultimately lead to new solubility arising from that break, right? And as the number of water molecules change, the solubility also changes with increase in temperature. So this is about the dissolubility curve. Common phenomena is fractional crystallization. Fractional crystallization is a phenomena in which we basically um, what do we call it? Fractional crystallization is a basic phenomena in which we remove impurities from a crystalline solid, such that if we take a crystalline solute which is having impurities, we dissolve it in a solvent, such that its impurities of the crystalline solute are more soluble in that particular solvent than the crystalline solute, due to which they that crystalline solute having less solubility than the impurities will be dissolved by heating it up, such that we'll be dissolving the hot crystalline solute with impurities within the solvent, due to which it will cause to hot crystalline solute with impurities will be dissolved in the solvent, due to which it will be dissolved, even though both of these are having different solubilities. But when we are going to cool them, the less soluble crystalline solid will be crystallized out, precipitated out, because of its solubility decreased as a result of decrease in temperature, while the impurities which are more soluble within the solvent will now tend to produce the solubilities will now tend to produce a structure. Now, these impurities being more soluble will now tend to remove, will now tend to also have their solubility decreased, but will not till that extent that they will be crystallized out, due to which the less soluble crystalline solute is crystallized out as our desired pure product, and impurities remain dissolved within the solvent after cooling the temperature. So this is what we call as a process of fractional crystallization. When it comes to pressure, pressure is not affectable for on solubility for solids and liquids. But if we consider the effect of pressure on gases, so at that moment, yes, it is affectable on gases, such that if we increase the pressure, then more number of molecules are present on the reactant side. Or if I were to explain through a gas, let's suppose if this is a solute, if this is a solvent, and here there is a gas, okay. So this is a gas, and if I, let's suppose this is a movable piston, gas molecules are there. And now whenever I'm going to apply high pressure, if I will be increasing the pressure, the increase in the pressure will cause the gas molecules to come closer to each other. The gas molecules will come closer to the surface of the liquid, due to which they will there will be more chances of formation of attractive forces between solute and the solvent, due to which the chances of formation of attractive forces between solute solvent will be increased, and ultimately the capability to dissolve within the solution will be ultimately increased as an increase in the pressure, if it is the case of gas. While if there is a decrease, then the decrease in the pressure will ultimately lead to less solubility in case of a gas. So this is all about today's video. Hopefully we'll meet again in another video.